Welcome everyone to the 10th lecture. In the previous lecture, what we have seen is the general solution of Airy's stress function in Cartesian coordinates, and we have also followed it up with one example. The example which we chose for Airy's stress function solution in Cartesian coordinates was that of a uniform loading on a beam which is supported simply at 2 points, right? And we formulated the boundary value problem, use the boundary conditions, use the general solution, and we have identified the solution. Now, in this lecture, what we will do is not something very different. It is a follow-up to the previous lecture. We will see what was the limitation of the previous solution. That's first thing. And then we will see how do we overcome that limitation, and that overcoming of that limitation, we will seek the help from Saint Venant's principle. Okay, so this is the objective of this particular lecture. It's a fairly short lecture because the concept is simple and straightforward, and we have already solved the general solution. So it will be a relatively short lecture, but the concept is useful in other examples as well. So this was, I thought of giving a short recap. This is the problem which we have solved. Right? We had a beam bending. We had a beam which was rectangular, right? And it is should be this should be 2b and not the entire one, right? So basically this guy is 2b, right? And it is rectangular in cross section, and there is a uniform load, which is load per unit length of p, right? And then we said, okay, mine is a rectangular three-dimensional domain, right? And then we have set the boundary conditions. We have started from Cauchy's traction. And on the top surface, we know that the normal was either top and the bottom surfaces, the normal was either plus or minus 1. And you know the corresponding relevant stress components. And then you went ahead, and for the problem, you have assigned the Tx to be 0, which means sigma xy there was 0. And at y is equals to b, should be Ty is equals to sigma yy, right? And that's how you got the stresses. And at the bottom side, Tx and Ty both are 0. Okay. And on the sides, x is equals to plus a and minus a. You know the normal is either plus or minus 1. And since there are no external loads, we have set sigma xx to be 0. And sigma xy, the integral of it all over the region, which is minus p to plus b, we have said it is p0 times a. Okay, how did we get this as p0 times a? Because the reaction at each support point, which are two support points, is p0 a by 2. Now there's a slight typographical error which is popping up here. Is p and p0 are the same. Okay, so p is equals to p0. Okay, they both are identical. Okay, and we have also said, since we are drawing the free body diagram, we have also said that you can accordingly construct the equation for moment. So we have used these boundary conditions, and we started with Airy stress function in Cartesian reference frame, and we chose a polynomial. Now these are things which we know. I just am giving you a short recap. And we also said we'll have to choose the number of terms based on how your loading distribution function is with respect to the length. And accordingly, we chose a function, right? We chose a fifth order polynomial, and we substituted it we used the boundary conditions, the definition of stresses, right? And we ended up solving quite a few number of equations, and this is the solution which we have got, right? We arrived at the stress function, which is a function of x and y as well as the load, and from there we identified the three relevant stress components. Right? Now, what is the problem with this solution? Right? At the beginning of the lecture, I have said that there is a slight issue with this. Right? So what is the problem? First, let us see the plus points. If I compare this with the standard Euler-Bernoulli beam theory, this is the solution for using Euler-Bernoulli beam theory. If you compare the sigma xx of both the terms, the sigma xx here and the sigma xx here, right? You will see that you're getting two additional terms, this 10 minus 10y cube and 6b square y, which do not appear in the Euler-Bernoulli beam theory sigma xx, right? And likewise, your sigma yy and sigma xy here are zero, whereas you do get some expressions when you use the theory of elasticity. Okay, so there's a plus side that you are able to capture more terms and more accurate than your standard Euler-Bernoulli beam theory. But does it mean we should not use Euler-Bernoulli beam theory? Euler-Bernoulli beam theory is useful. In fact, skyscrapers have been built. Many buildings have been built. Every beam which you have seen so far has been analyzed using Euler-Bernoulli beam theory. There's nothing incorrect about it. It does make some approximations. Which one? The Euler-Bernoulli beam theory does make some approximations. The primary approximation is that planar sections perpendicular to the cross section remain planar. That's the first one. And second, while deriving Euler-Bernoulli beam theory, we have made an assumption or saying that the length of the beam should be much longer than the cross-sectional dimensions. And here the length of the beam was 2a. So if Euler-Bernoulli beam theory has to be applicable, 2a must be much greater than 2b, which basically means a is much greater than b. In fact, if you look at any beam, either it is the railway track, the rail in the railway track, or an overhead beam in a beam supporting the RCC, RCC as in the reinforced cement concrete roof, the roof made by an RCC. In all these cases, you will see that your length of the beam is actually much longer than the cross-sectional dimensions. So that is the success of Euler-Bernoulli beam theory. Now you guys are learning advanced things. And in that we have used theory of elasticity and found that no, you don't have to be limited by Euler-Bernoulli beam theory, but there are these additional terms. You also do get a sigma yy and you also get some shear stress, right? That's what we are predicting. So these are the plus sides. Now, so what? So what if we are able to capture more terms than Euler-Bernoulli beam theory, what is the problem? We'll see what the problem is. First, the first point here is already discussed, that we are able to get more terms, although the original beam theory is reasonably good. Then the second point is the boundary conditions on the top and bottom surfaces, which is y is equals to plus b and minus v, are identically satisfied for the solution which we have got. The solution which we have arrived at using Airy stress function formulation, that solution is perfectly matching the boundary conditions. However, we have actually specified weak boundary conditions at x is equals to plus a and minus a. Remember, we have specified at x is equals to plus a, we have said integral sigma xy dy, integral ranging from minus b to plus b, is nothing but p0 a by 2. But if you draw the free body diagram, you will see that actually on the other side, on the left and on the right hand sides, which is at x is equals to plus a and x is equals to minus a, you do not have any shear stresses. That's something which we have done. Why did we set it equal to P0 times A or P times A? That is the force which is transferred by the reaction into the beam, right? And that we have said, okay, that is going as a shear at the ends. Is that, and we have said it is not just at one point, it is being transferred all through the cross section from minus B to plus B. And that is why we have set an integral kind of boundary conditions. Such kind of integral boundary conditions are also called as weak form or weak boundary conditions. Okay. Now, I would just rewrite or revisit the boundary condition, whatever we have said. This was the beam, right? And at this surface, you had sigma yy dx is equals to minus p, and at the same surface, sigma xy is equals to 0. And on the bottom surface also, sigma xy is equals to 0. And here sigma yy is equals to 0. Now you guys will have to bear and excuse my writing on a new graphic screen. Okay. But I'm sure since this is something which you guys already have content on. So this is only a recap, or and this is y is equals to minus b to plus b. Right. And on both these surfaces, on this left hand side as well as this right hand side, there are only two kinds of boundary conditions, which is sigma xy dy minus b to plus b is nothing but p times a, which is actually transferred at this point, at these 2 points, right, by the simply supported points. Likewise, the other condition is sigma xx dy minus b to plus b is 0, because there is nothing acting along the horizontal x direction. Right? This is the figure which you had, and these are the weak boundary conditions. Right? Sigma xy dy minus b to plus b is equals to pa. Whereas realistically speaking, there is actually no such term. I mean, the actual force is acting at the bottommost, the bottom right corner. Right? So we have sort of given an weak condition to solve the problem. Now, in this lecture, what we will see is how do we get rid of this weak formulation? Why not? Why should I simply not give anything else? So that is the thing which we will try to do. Okay. So let's proceed. So the summary is that you have the condition which is exactly the boundary conditions which are exactly satisfied on the top and bottom surfaces, which are y is equals to plus b and y is equals to minus b, whereas they are weakly supported, weakly satisfied on the at the left and right hand sides, which is at x is equals to plus a and minus a. We'll take a slight detour, or we'll just pick up this concept of Saint Venant. What this concept says is the following. Let's say there is a huge block, say 10 feet by 10 feet by 10 feet. Let's say there are two such identical blocks. And let's say you have a duplicate person. Right? On first case, you will go and sit on the rock on this block at one point. Somehow you have managed to sit on one point. Now, in the second case, instead of sitting on the block at one point, you have somehow distributed your weight. You have somehow distributed your weight. The easiest way is, you probably filled it with some water region. There's some water, and on top of the water, you put a thin plank, and you are sitting on the plank. Okay, and because there is water here, every point is equally being stressed or equally loaded, unlike the first case where it is a point load. Saint Venant's principle tells us the following. Let's say your objects are large, or even if they are small, this is what it says. Let's say you're applying the load around this region, which is on the top surface region, right? And you're applying identical load, right? Here the load is P and here the load is P. The only difference is here it is a point load and here it is collectively the distribution small p of x dx is equals to capital P. Whereas on the left hand side, the load distribution is integral delta of x minus delta of x capital P dx. Right? The overall loading is the same on the same region, right? Two things here. The overall load must be the same, and there should be at the same region. Okay, it cannot be like in the first case you load it on the top surface, and in the second case you may have a distributed load, but you say you are applying it at some other region. No, in such cases Saint Venant principle is not valid. Okay, you are applying the same amount of load in both the cases, and however the distribution is different. Okay, and in such a case, if you look at points which are far away from your point of application of load, let's say this distance is large. Okay, this d is large. Okay, in those cases it does not matter whether you are applying a point load or whether you are applying the same load in a distributed manner. Okay, it need not always be a uniform distribution also. You could have had any kinds of distribution. All this principle says is, you may have, if you have identical loads locally, okay, and whether they are distributed in whichever smoother manner, far away from the point of application of the force, it doesn't really matter where you are applying the load. That is what Saint Venant principle says. So we will use this, and let us see how we can slightly tune our problem to get the precise solution. Okay. Another thing which you may notice is, I would request everyone to, we have identified the three solutions, right? Sigma xx, sigma yy, and sigma xy. Now, I have already declared that sigma yy, or on the top surface, as in at y is equals to b, and at the bottom surface y is equals to minus b. I have said that the boundary conditions are already satisfied at y is equals to b and y is equals to minus b. Please check it. Then the second check the boundary conditions on x is equals to plus a and minus a. Check if they are satisfied, right? Further, do the third check, which is an essential check, which is at the top right point, which is at x is equals to a and y is equals to b. At that point, that particular point should be satisfied by both sets of conditions, right? At that point, x is equals to a and y is equals to b. It should satisfy the boundary conditions from the line x is equals to a, and it should also satisfy the boundary conditions as posed on y is equals to b. Likewise, the remaining three corner points should satisfy two identical boundary conditions. Sorry, no, should satisfy two boundary conditions, two different sets of boundary conditions. Please verify it. If you try to verify it, you will realize that they are actually not identically satisfied. Okay, so that is the reason we are trying to apply Saint Venant's principle and trying to overcome this minor sort of approximation which led us to such a formulation. We are trying to overcome that with an additional corrective term. Okay, so please verify the boundary conditions on each face and also ensure whether the boundary conditions are satisfied on the corner points. Okay, let's proceed. So I'm going to slightly remodify my diagram. In the previous lecture, or even up till now, we had the beam, and the overall loading we said anyway was a uniform load. So the total load is 2p times a. Now, just so that the additional boundary conditions at the corners are satisfied, okay, this is what we are going to do. On the right hand side of the diagram, you see that sigma yy and sigma xy are set to 0 on the top region. Whereas previously, what did we do? Previously, we said on the top surface, sigma yy is equals to minus p. The integral of sigma yy dy is minus p, right? And sigma xy was 0, right? Tx was 0, so sigma xy was 0. Now all we are saying is, let me redistribute my load slightly such that I'll have some regions, some small region where sigma yy and sigma xy are both 0. Okay. So that my conditions are satisfied everywhere. That is the only change that we are doing. And everything else is the same. Okay, this is the additional term sigma yy is and sigma xy are 0. Okay, and since I am looking for a corrective solution, I am going to create or look for one more Airy stress function, which is basically which should be added to your original Airy stress function. Okay, so I'm choosing a function of this form: f of y times exponential minus lambda x. Excuse me. So I'm choosing an Airy stress function, which in Cartesian frame, of course, which which can be written as function of two independent variables, which is f of y times epsilon minus lambda x. And it is understood that when I'm using a minus sign, it is better I also specify that lambda is greater than 0. Imagine what kind of function epsilon exponential lambda exponential minus lambda x is. This is x, and if this is my function exponential minus lambda x, it is a decaying function, right? So I'm seeking a solution such that my function vanishes as x increases. This is in line with the kind of boundary condition that we have chosen. What do we need? What is it different that from our previous lecture or the previous solution that we solved? Here locally the solution should die out, right? So that your other boundary conditions are in place. So that is the reason a decaying function has been chosen. Okay. Now this is also an Airy stress function, which means this should also satisfy the biharmonic equation. Okay, which means if I substitute for phi as f times exponential minus lambda x, I would end up with the following function. So even f of y is dependent on lambda. Okay, so your overall function phi 1, I should say, is nothing but phi 0, which is the solution which you obtained in the last lecture, plus this phi, whatever phi we are using now. This is your actual overall stress function. Okay, we are looking for just this corrective term. Phi 0 is something which you have already identified. Okay, even here it should be del power 4 phi 1 is equals to 0, and this would imply del power 4 phi 0 plus del power 4 phi phi is equals to 0. Del power 4 phi 0 is anyway 0. That is the reason we have set this function to 0 and obtained this particular expression. You see that f of y is actually dependent on lambda. Okay, so now let's use the boundary conditions. So the boundary conditions and x is equals to plus a plus or minus a are the same as what it was before, and at y is equals to plus a and at y is equals to plus b primarily, where the loading is there, you have sigma yy and sigma xx as 0, and at y is equals to minus b, you anyway have sigma xy as 0. So the boundary conditions are not something new to you now. Okay, let me see if I can erase this ink tools. Looks like I can't. But yeah, so the boundary conditions at y is equals to b have this slight correction, which is sigma yy should be 0 and sigma xy should be 0. Right, and at y is equals to minus b, anyway, even in the previous case, we had sigma yy and sigma xy are as 0. So now one short note which I want everybody to pay attention to is on the behavior of f of y. What kind of function is e1 cos phi? Is it an odd function or is it an even function? Cosine function is an even function because cosine of minus theta is nothing but cosine theta. So this is a function which will be symmetric about the y-axis. Whereas sine of a function is always sine of a variable is a function which is an odd function. As in sine of minus theta is minus of sine theta. Right? So a1 cosine lambda y is representing a symmetric function, whereas A4 y sine lambda y, rather let's not go till A4, A3 sine lambda y is an odd function, which is an asymmetric function. Likewise, if you examine the second term, A2y cosine lambda y cosine lambda y is an odd function, and y sine lambda y is an even function. I'm sure you can verify whether y's cosine lambda y is an odd or an even function, but I'm giving you the answer. Y cosine lambda y is an odd function. Y sine lambda y is an even function. So if you see, the function f of y is a summation of odd and even functions. Okay, which basically means they are going to represent the symmetric and asymmetric parts. So that's what I wrote. So the terms containing A1 and A4 account for the symmetric solutions, and terms containing A2 and A3 account for asymmetric solutions. What is symmetry, asymmetry? What am I suddenly talking? What exactly is F representing? F is representing phi. And what is phi actually? Phi is representing the stress function, right? So imagine there is a beam. You can bend a beam symmetrically as well as asymmetrically, right? So we will see, once you start plotting things, you will realize the importance of symmetry and asymmetric solutions. But for now, even without realizing that they are symmetric or asymmetric, mathematically you can still proceed. This asymmetry, symmetric and asymmetric forms show up when you plot the stresses or when you plot the deformations. Okay, you don't have to really tighten your head against this, what is this symmetric and asymmetric. Once you plot your solutions, you will realize it. Or even towards the end, I will try to show you what this symmetric and asymmetric are. Or let's see if if we can go back and quickly do this with an example. Give me a second, please. Yeah. See, if let's say I have a beam, right? Simple beam. Now, when it is deformed, I can deform it in various ways. And once in among those, one such deformation can be, so this is your beam. So this was your original beam and this is your final beam after deformation. What happened here? If this is the central line, the deformation on the top side is upwards, whereas the deformation on the bottom side is downwards. If I draw the central axis here. So this is some kind of a symmetric deformation. There is asymmetric deformations which you are usually, so this is symmetric deformation. This is something which is very common in what is called as Lamb waves. Something, if you do a wave mechanics course, you will actually see this. I mean, this is Lamb wave. Asymmetric solution is something which most of you know. I mean, you take a scale or a beam and bend it in every manner which is possible. So this is how your beam will look like. Right? It is, I mean, if somebody gives you an elastic cord, I'm sure this is the easiest way in which we can bend it multiple times. So this is the asymmetric bending. Okay, so the form of f of y is actually telling us that your solution can be expressed as functions of asymmetric and symmetric solution. Your general deformation would be a linear combination of these two, maybe some alpha 1 times this solution and some beta 1 times this solution. So that is what, so your general deformation can be anything, right? This was your original beam and this could be your final beam shape. I have exaggerated the drawings because just to show the symmetric and asymmetric deformations, but you must realize, keep in mind that we are dealing with small deformations. Okay, so imagine instead of this high amplitude, you have to imagine something like this kind of a deformation. Okay, here if you see the displacement, they are asymmetric, not symmetric. Okay, so this is what the symmetric and asymmetric solutions mean. Okay, so we have our general solution, and we also have the form of the dependence of the function f of y, and we know our boundary conditions. So let us go ahead and apply these boundary conditions. Okay, so this is my solution and the boundary conditions are known. So I will go ahead and apply these boundary conditions at both the places y is equals to b and y is equals to minus b. And what is sigma yy? Sigma yy is dou square of phi by dou x square. So you will get two equations, one for y is equals to plus b and one for y is equals to minus b. Right? And similarly, using the sigma xy is equals to 0 condition, you will get two more equations for f at plus and minus b. So you have four equations, and how many unknowns are there? A1, A2, A3 and A4. And what is lambda? Is it a known or is it an unknown? That is also an unknown. So we have total five unknowns, but so far we have only four equations. Let us see what we can do with it. Okay, so there's four conditions, four boundary conditions led us to four equations. Okay, you can rearrange them and you can write them this way. Okay, so algebra which I have skipped, you can cross check it. So the first two equations have terms a1 and a4, and a couple of slides ago what did we say? A1, the terms containing a1 and a4 were leading to symmetric solutions. Right, and if you see the last two equations, they have a2 and a3, and these two terms were actually a2 and a3 were the coefficients of the asymmetric functions. Right, a1 and a4 were the coefficients for the symmetric functions, and a2 and a3 were terms corresponding to the asymmetric functions. So although we have four independent equations, you would see that the first two is a set and the second two is a set. In the first two equations there is no a2 and a3, and in the second two equations there is no a1 and a4. So we have basically two sets of uh, homogeneous equations, each set containing two equations. And for you to have a solution, what should be the case? The determinant should be 0. So that's what we are going to set it as. Right? The symmetric solution, if I take the symmetric solution, which is the first two equations, for if at all I need to have a solution, the corresponding coefficient or the determinant of the coefficient matrix should be 0. And when you do that, you end up with one equation, which is sine 2 lambda b is plus 2 lambda b is equal to 0, which means the solutions, your lambda should have only specific values as given by this equation. What happened to this? Yeah. Okay. How do you identify lambda? There are various ways. Uh, if you see, all we are saying is sine x plus x is equals to 0. And we need to identify the values of x and divide it by 2b. Easiest way to get the solution is to plot it. You plot these functions, you plot this function, you say you call this function as, say, let's not call it f, let's call it, say, capital G of lambda. Okay, you plot this function and you see where it is intersecting the x-axis, you get the roots, and those roots are nothing but lambda sp. What is the other way? The other way is use any numerical method, say Newton-Raphson method, for example. One of the first methods to identify roots of an equation. So you can use Newton-Raphson method, right? And you can write a program. Okay, so there are various ways to solve this kind of equation, either numerically or graphically. Likewise, for the asymmetric case as well, you will get one more equation when you set the determinant of the coefficient matrix to be 0. So here also you will get corresponding set of eigenvalues, right? Only for these values of lambda, you can have a solution. Otherwise, there is no solution. Okay. So your overall Airy stress function, which is, I mean, this, when I say stress function, this is that corrective stress term, is a function of symmetric solutions as well as asymmetric solution. Slight typo here. It is APS and not PAS, right? Asymmetric solution, sorry, ASP, asymmetric solution or asymmetric values for P. right? And whereas where you know your symmetric and asymmetric solutions. Okay, there's a bit of typo error here it is, but I hope you guys don't pull strings out of this. Okay, one, the lambda SV standing for the symmetric eigenvalues or solutions which correspond to symmetric functions, and lambda ASP or lambda ASP is corresponding to the solution are the eigenvalues for the asymmetric solutions. So your general solution of the corrective function should take this form, this particular form. How do you identify CP and DP? You use the remaining boundary conditions. So far in deriving this, I have not used the boundary conditions on x is equals to plus a and minus a. Okay, here you, like just the way we have solved while in the previous problem of beam bending, how should we choose the number of terms? Right, we chose it based on the how the load distribution function was. Here also you will need to choose an appropriate number of terms and then identify your corresponding C1, C2, C3, so on, and D1, D2, D3, so on. Okay. The idea of this particular lecture, or the purpose of this lecture on Saint Venant's principle, is to show how you can refine your solutions even further, accounting for precise boundary conditions at every point in the space, right? At every point in the boundary space. That's what I mean. Okay. And towards that, we have seen for this kind of loading, which is loading only on one side or even on the opposite sides. So long as it's on opposite sides, this formulation should be fine, right? And we chose a particular form for the Airy stress function, which is variable separable functions f of y and epsilon, sorry, exponential minus lambda x. And we also said, why are we choosing an exponential minus lambda x? Because we want a decaying solution. This is a corrective term. We want that solution to decay as it goes towards x is equals to plus a and minus a, right? And we used the biharmonic equation, and then we applied the boundary conditions of sigma yy and sigma xy being 0 at y is equals to plus b and minus b. We ended up with 4 equations, and then from there we have already correlated it to the asymmetric and symmetric solutions, and that's why you have two independent sets of eigenvalues, one set corresponding to the symmetric solutions and the other set corresponding to the asymmetric solutions. Okay, the idea was to give you the formulation. How do we solve in case if you want to, if needed, whenever needed. Okay. And in the next class, we will try to see how do we incorporate body forces. So far, all the problems that we have solved, filament problem, beam bending, uh, right? These kinds of problems, we have not used the body force. So in the next class, we will see, next lecture, we will see how do we incorporate body forces. And following up, we will learn another kind of technique, which is based on integral formulation. So far, we have the techniques we have saw was an Airy stress function, solving differential equations, right? We have sought a variable separable solution. We have sought a polynomial kind of solution, and then we will see how we can use integral transforms, which is actually a very powerful technique and very powerful yet simpler in implementation. Like you have seen the amount of rigor that went through while we were solving the general solution for Airy stress function in polar coordinates, right? And likewise with even the polynomial solution. Whereas if you see integral formulation, the formulation would be relatively simpler and relatively easier, much easier, and hence easier to apply. Okay, so I will see you all in the next lecture. Until then, I will sign off. Okay, bye then.